Uh, Hello everyone. Uh, this is Praveen. I'm a student of uh, Robin Batch in. Actually, where I'm tasked to complete one of the projects that are assigned to our batch, and out of this, I choose this one, the maze solver. Uh, the aim of this maze solver is given here is to build a Python program that runs as a command line tool. So it should take input and output file name as command line arguments. Using the square matrix in the input file, we should generate the path to reach the end of the maze and put it in the output file. If the maze is unsolvable, we should return -1. Okay. So uh, the way I did is here. Actually, the link for what I have done, the entire process, the instructions to execute the file that I created, and the way my file works, and the output that I will get is everything described here in the readme.imd in my projects. And this is the executable file, and this is the Python file. Okay, and for your convenience, first I'm going to show the Python version of this file, and this is the Python version. Initially, I created a graph, the class graph. I initiated the following attributes: a graph containing the default list. This is I used this attribute to save the nodes and their neighbors in the graph. The edges. Uh, this this attribute has been used to save the distance between the two edges, the two nodes in the graph, and this self-dot vertices has been used to store the number of the different nodes that are present in the graph. And this prev.vertex has been used to store the previous vertex of any particular graph when we are traversing through the graph in the following path. And these are the main methods that have been defined in the class graph. Add edge is connected, and Dijkstra, and the source to destination path. Uh, what the user will see is actually user won't see anything. The user will get simply one file like this, server.command. So what user can do is like he can simply double click on this file, and what he can do is he can simply enter the order of the matrix, suppose say 5, and he can simply view the input of the matrix in the form of binary numbers with space separated like this. Suppose it is better if we have more connected graph. So defining like this. Okay. See, this is the 5 by 5 matrix, a randomly defined 5 by 5 matrix with all zeros and ones. And this represents a maze, like wherever ones are there, that is an open path, and wherever zeros are there, that is blocked path in the maze. So one can traverse through from this starting node to any particular node if it is connected. Basically, in this graph, it can traverse from this node to any other node. Suppose uh, we will enter the this node. The position of that node is 0, comma 4, and I will enter the starting node. Suppose whether these two nodes are connected or not, and we will whether we get the output or not, we will check this 0, comma 0, these two nodes. Now the session has been concluded, but we have to see and verify the output. To verify the output, we have to go to the output file that is there in the defined in the code. We will go to the output file.txt. Actually, it is not connected. Why it is not connected? Okay, 0, comma 4. This one. We will have to define this one. Let's try again. The same graph with numerics as well. Okay, let's see. Now we'll check. Now the position of this is 0, comma 3, and the position of this is 0, comma 0. So 0, comma 0. Now enter. Now we will verify whether there is an output or not. See here, we'll go to this, and here they have the output from this node to this node. Likewise, we can check the connectivity for any node from any node. The path really exists between the two nodes, then this file will return the path. Otherwise, as we have seen earlier, it will return -1. Now let's dive into the Python code of this. Sorry. Okay, we'll go to this. Now what are all I have used for this? The key things that I have used for this is connected thing and the Dijkstra's method. Why I have used this method? Since whether from the user can give any random input, any random input matrix, we don't know whether that any node that user has given is connected to any other node that user has given. So first we have to check the two nodes are given, two nodes that are given by the user are connected or not. So we collect the two nodes from the user using this method, source to destination method. Here source is u and destination is v. When we call this method from here, and we go to this. First, we will assign all the vertices as vertex visited is equal to false, so that no vertex has been visited previously. We define q, and initially we append this list with u, the source node or the starting node. Now the connected vertices, we define another data type connected vertices. and we define it as set. Now, until there is an element in the queue, what we will do is we will pop the first element of the queue, and we will what we will do is we will go to the neighbors of the queue. If any neighbor in that if any neighbor of that node is not visited, then we will append it to the queue. And what we will do is the node that we have visited will be assigned to true. And similarly, we will add connected vertices. We will add the node to the connected vertices, and we will update it. And we will run it until the entire all nodes are visited or connected. Then, if the source node and the destination node are in this set, then only this is connected method will return true. Otherwise, it will return false. So, if it returns true, then the following lines will get executed. In this following lines, we will call the Dijkstra method, which we have defined on top of this method. In this method, what we will do is same. We will use the Dijkstra algorithm, like we assign all the nodes that are different from the source node. That is, the distance from the source node to any other node is infinity. Here we cannot define infinity, so we use 10 power 9. And we, as earlier, use this vertex visited thing. So we also define the graph, then we also define vertex visited dictionary, and we assign each vertex whether it is visited or not as false. Now, what we will do is we will run the loop. We will check for the node, and we go to the neighbors of that node, and we will update the distance of the neighbors of the node from the given node. At the same time, we will also update the previous vertex of the neighbor according to the shortest distance that we have obtained from this function, from this loop. Then we will obtain previous vertex for many different neighbors in that particular node. Then what we will have to do is we have to find the next node that has to be visited. Here, after visiting a source node, what we will do is we will sort the neighbors according to their distance, and we will visit the next shortest node, the shortest distant node from the source node. If all the nodes, all the neighbor nodes of the source node have been visited, then what we will do is we will go to any previous vertex. If there are any remaining neighbors are there that are not visited, we will check that condition. If all the neighbors of any previous vertex have been visited, then what we will do is we will go to the node that has not been visited, and also the distance from the source node is less than the infinity. Here infinity is this one, 10 power 9. Then we will run this loop again and again and again until all nodes are visited, and then we will obtain the dictionary of the nodes of each node in the form of previous vertex, and here we will assign it to this previous vertex. Then we will convert it into the list, and then we will check the length of the list, and we will again run this loop. Hmm. Why we run this loop is that we obtain the list in the form of tuples. So what do we have to do is we have to arrange this all the uh, nodes in specified uh, direction, like in the from the source node to the destination node. In that direction, we have to arrange this list, and then we have to convert this list into the set, so that it is easier for us to verify whether particular node is there in this set or not. And why particularly we use set is it takes only order of constant time to check whether a particular element or certain thing is there in this set or not. For when coming to list, it will take order of n time. That is, it will compare as many number of elements that comes before particular thing to give the result. Now let's go to the driver code. As we have defined the class earlier, now we are instantiating the class with this object G graph, and here we are also like opening the file in the text mode, this input file, and we are writing this file via the order of the matrix. Like here I didn't write anything. You can write the order also. Like you, for the convenience of user, you can like uh, write order of matrix in the in between the first phase, so user will get to know what to enter here. And also for after writing this, we have to close it. Now we have to open it in the read format, and we have to assign this value to some variable, so that we and this variable, when converted into integer, we can take the input from the user. We can take the input matrix from the user for those particular number of times. So the next time we open the file, we open it in the form of append mode. Why we have opened it in the append mode? Because we do not want to destroy this input. Whenever we open the file in the input form, this write form, the uh, previous data that has been defined on that input file will be completely erased, and the new data will be saved. But while it is opened in the append form, the previous data will not be erased, so that we can safely enter the input matrix in the next lines. See here, for the number of order, the range of order, we are like inputting the data, feeding the data to the file. Also, in addition to that, we are also entering the source node and the destination node line by line. And then we finally close the input file.txt. Now again we have to open the input file.txt in the read mode. Then we define input matrix in the nested list form actually. And the main purpose of this code is to generate the input matrix in the list form, nested list form. Here uh, we read each line, and in each line we generate a list of binary numbers, and then what we will do is we will append this to the input matrix. So input matrix will be in the nested list form. And again, what we have to do, this part of the graph, this part of the code is to give the input to the object graph, or we have to generate the graph, and all the we have to provide data to this graph, so we can run the entire source code. See here, we are generating this, and then what we do is we are also reading this uh, the source node and also destination node here, this part of the file. Why I run this part is to know the number of lines in the code, and the last two lines will be assigned to the source node and the destination node here. So I converted this source node into the tuple and also destination node into the tuple. Now what I've done is here I call this source destination uh, method using this object G object by passing this source node and destination node. After doing this, all these things previously discussed them, we will get an output. Now, if the returned value is in the form of set, if the type of this is set, then only we will print the par or we will print the matrix, and in that matrix we will print the par. Otherwise, we will return whatever that is there that has been returned by the this source to destination method that is defined in the class graph, and we will close the output file also. We can also verify the output file, input file, as we have verified the output file. Let's check it. It should be in the yes. See, if you compare whatever that is there, not here. This one is sorry, that is defined in the desktop. Actually, what are the files that will be created, like input file.txt or output file.txt, will be saved in the documents. That is the home. So it will be like this. See, you can compare the input matrix as well as you can compare the output matrix. Sorry. I am not getting this. Yeah, here it is. See, these are the things that we have done. So this is very simple. Actually, this is very simple and it is very easy also. But why I have chosen this project to do is uh, it's not only because I have chosen this project that because it is very simple, but it has very potential applications uh, in data mining and the data analysis, uh, like in the Facebook or in the Instagram, that we can use or we can scale up this kind of code to identify if particular person is friend of this particular person or if particular email is anyway connected to this kind of user or anything. We can we can identify a node, and we can if we identify two nodes in particular code matrix, then we can see if they are connected in any way, and if they are connected and how they are connected. Maybe what we see here is simple, so simple like a hello world, but the application part is so much, so huge. So that's what I want to show to you people. Thank you very much for listening to me. Thank you.